Electricity and power in general is a very important and capital-intensive industry, and that's true for both current power plants that are creating electricity, but also the solutions that can hopefully address some of the carbon capture. Many of the emerging approaches, like direct air capture, will begin to have an increased level of prominence in the discussion.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about carbon capture using selective gas absorption. My guest says they have developed a compound that can pull CO2 out of air, natural gas, or exhaust gas from a power plant. At the time of this recording, my alma mater, LSU, is on their way to the college football playoffs.
And that will do it. West over East, and LSU is 13-0. Geron.
What a great season and a proud moment. I probably watched more games than I did as a student, but what I noticed during those games were the commercials from ExxonMobil touting one of my other favorite things, carbon capture.
Plants capture CO2. What if other kinds of plants captured it too? We could help lower emissions. Carbon capture is important technology, and experts agree. That's why we're working on ways to improve it.
These ads were inescapable, and so I figured I'd track down one of the partners Exxon is working with to improve CO2 capture. We've covered guests on this show before. I've told you about my experience leading a trade association in Texas. Carbon capture is challenging, expensive, and it's one of the only clean energy technologies some in the public just don't support. I get that you don't like coal plants, for instance, but if you could capture carbon from even a fraction of those plants, you could more than offset the gains made by renewable energy in the past decade. My guest says he started down this road because he wanted to do something about CO2 emissions. And he also understood that the world is not going to get to what we call net zero carbon emissions without a capture solution for fossil fuels. The underlying technology, he explains, is metal organic framework technology, or MOFs. Essentially, these are ultra-high capacity sponges for gases. In this case, you pass air through them and they'll trap the CO2. Once the MOFs are full of CO2, you heat them up and that releases the stored carbon. My guest says they've been working on a way to maximize this design. Right now, the material is molded into a white pellet shape. They say they are also trying to find the most efficient way to trap and release the carbon. Carbon capture's biggest problem has been trapping CO2 without an enormous energy penalty, what they call parasitic load. My guest believes waste heat from a power plant could play a role in the desorption end of the cycle. I've said before that CO2 emissions control should be both a filter and a vacuum. With this technology, we could also see an energy-efficient means of pulling CO2 directly out of the atmosphere. My guest today is Dr. Thomas McDonald, co-founder and CEO of Mosaic Materials, a MOF developer based in the Bay Area. Thomas and his co-founders developed the underlying technology while at UC Berkeley. In August 2019, it was announced that ExxonMobil had reached an agreement to explore Mosaic's carbon absorption technology. Mosaic has been operating since 2015. We discussed several avenues for their technology, including post-combustion carbon capture, which is bolting carbon capture onto the flue gas end of a power plant. Mosaic is also developing a process for removing CO2 from natural gas. I hope you enjoy my conversation with Thomas McDonald. We're here with Dr. Thomas McDonald, CEO and co-founder of Mosaic Materials. And Thomas, I'm watching college football this year, and two great things are happening. One, my LSU Tigers are going undefeated, and two, ExxonMobil is airing these carbon capture commercials for a broad national audience. We'll get to your relationship with them in just a second, but watching those commercials, did it occur to you that football fans and whoever else were getting the message that carbon can efficiently be captured?
Jay, thanks for having me on. I really hope so, because I do believe that if we're going to solve global warming, it's important that the public become more aware about where energy and carbon emissions come from, but also what options are available needed to get us to net zero. I'm a huge believer in solar and wind and believe that they'll continue to grow at a rapid pace, but I also believe that fossil fuels are not going away anytime soon. And thus, it's really important we find solutions that can effectively deal with the CO2 emissions that we know we're going to emit for the next century. I believe the world will be in a much better place to deal with climate change once technologies can effectively capture or remove CO2 emissions, and once those technologies become scaled and commercialized. So these are some really tough applications, but there's definitely no more important problem to be working on today. And that's a really important part of what Mosaic Materials is doing.
So take us to the beginning. You're at UC Berkeley, and I take it you developed this technology, and then the company started out of that, right?
Correct. I started as a chemistry grad student, and I was pretty lucky because I knew exactly what I wanted to work on going into grad school. There were these beautiful materials that were coming out in the literature called metal organic frameworks, or MOFs. And I've always been really interested in trying to come up with new technology solutions for climate change. I was really lucky to join the lab of Professor Jeffrey Long at UC Berkeley, and Jeff's now one of the co-founders of Mosaic. What we were working on for a long time was this fundamental studies about how does carbon dioxide interact with these materials. And around 2011, 2012, we came up with this really novel series of materials that it separated CO2 by a completely unique mechanism, something we termed cooperative absorption. And it took a number of years of my PhD to ultimately sort of fully elucidate how these materials were working and how do we control it. But the results we were seeing from an applications perspective, especially for things like carbon capture, were really quite incredible. When I finished my PhD in 2015, I came on board and with Jeff helped co-found Mosaic Materials and have been doing this now for the last about 4.5 years.
I think in my mind, before I saw these MOFs, these metal organic frameworks, and it looks like a big container of shipping peanuts, how big are they? Are they like aspirin? How big are they?
I think the pills you're probably referring to is just one way of making a pellet that you could use for an industrial scale separation. The core technology itself is basically like salt. Ultimately, it's a highly porous solid that when we synthesize, it comes out of a reactor as a straight up powder. Probably those tablets you're referring to would be the equivalent of making sugar into a sugar cube. The way these materials actually separate CO2 is they're basically like sponges for the gas, where on the inside of the pellets is actually mostly empty space. So if we were to move air through the pellet at really high speeds, the CO2 will be stuck behind and the rest of the gases will continue to go through. If you're just using the powder and you're moving air really fast, the powder will blow away. So that's kind of why we make them into little pellets, just so they will stay in a reactor better. But you can similarly shape the powder into any number of forms and structures. I mean, it's a really important part of the engineering side of what we're doing.
So the air, the flue gas would pass through these pellets, and then the CO2 would be caught in them because there's a lot of surface areas, a lot of porosity there. How does the CO2 get released? Do you heat them up?
Exactly. In the case of carbon capture or something like direct air capture, the easiest way oftentimes is to use temperature. The capture process is actually spontaneous, and it's spontaneous because it releases a lot of heat. If you were to actually feel these pellets absorb CO2, you would notice the heat coming into your hands. Ultimately, to get that CO2 back out, you put in heat either through steam or through some other source, hot pipes, and once you get to a critical temperature, all that CO2 will come back off and you'll be able to collect a pure stream of CO2. Carbon capture is usually tied with some sort of sequestration or utilization, where the goal of our technology is to provide a pure source of CO2 to either then transport that CO2 and bury it underground or potentially to convert it into some sort of fuel. But our technology is effectively looking at the capture side. And one of the key things we do is the amount of heat, the amount of energy that's required to get the CO2 out of these pellets, because you would want to use them hundreds of thousands, if not millions of times, is a lot less than other technologies. So that's really one of the key defining characteristics of what Mosaic's technology could do. Bring down the amount of energy required to capture CO2.
The flue gas is usually very hot, right? So would you have to bring the flue gas temperature down, run it through your system, and then heat the pellets back up?
A lot depends on where your flue gas is coming from. Coal flue gas, especially in the United States, starts out a little bit colder because oftentimes, say, the sulfur removal processes that happen upstream of that are already sort of chilling that gas. But yeah, normally you'd bring it down to somewhere around 40 to 60 degrees Celsius. I usually think in Celsius more than Fahrenheit, sort of my chemistry training. And then that's usually sort of the sweet spot for most carbon capture technologies on the capture side. Once your material has been fully loaded with CO2, you need to find some way of bringing heat into the materials themselves. You can do it by either having multiple parallel beds. One bed is filling up with CO2, while another bed, the CO2 is being released, what we typically call desorption. Or you can have some sort of moving bed configuration. Maybe it's fluidized bed. I know a number of people work on that technology, where ultimately the goal is to then take whatever the material full of CO2 is and effectively heat it up to then release the CO2. Once it's at high temperatures, collect it, and then you cool it back down, and you use that same material to get the next batch of CO2 out. A really important part of the engineering work that goes into the applications we're doing is what is the most efficient way of heating up and cooling down that material, usually as fast as possible.
Yeah, no doubt. I worked in water treatment. Kind of reminds me a little bit of ion exchange, not necessarily the chemistry involved, but just this idea that you max out the bed of media that you're using and then you have to flush it out.
Absolutely. And in this case, what's nice is that because you can use heat in the case of carbon capture, if you have pressure available, you can capture and release through changes of pressure. It's usually quite easy to get a concentrated stream back out. And it's really about balancing what is the most cost-effective, energy-effective way of doing this. Because one of the hardest parts about carbon capture, especially from power plants, you don't want the carbon capture side to reduce the efficiency of your power plant too much. It's one of the traditional drawbacks of existing technologies is that they have this huge what's called parasitic effect. Our goal is to use new technology and new approaches to reduce that parasitic effect on the power plant. The more efficiently we can drive this regeneration process, the lower the cost of capture can be from any number of gas streams.
Yeah, that's the name of the game. I love doing these episodes because I don't feel like they get discussed enough. I was executive director of a group called the Clean Coal Technology Foundation of Texas about 10 years ago. Of course, we don't really say clean coal anymore, but there are several ways to capture CO2. From what I remember, there were membranes, amines, some catalytic technologies out there, but you talked about this parasitic load. They were expensive and they were energy intensive. So what really has changed here? I think there's a lot of old thinking going on here as far as the parasitic load and the cost.
Absolutely, the technologies have just gotten better over the last decade. And I would say that's true of both amines, membranes, and what most people call solid sorbents or just sorbent technologies. And that's what Mosaic works on, is a sorbent technology approach. Part of that is new engineering approaches, and a lot of people have spent the last decade coming up with more efficient ways of building plants and operating them. But a lot of it has also been new fundamental discoveries. I would say that's especially true on the membrane and the sorbent side. What's really unique about Mosaic's technology is that it actually binds CO2 using this cooperative absorption mechanism. And that's really important because the capture and release profile is very different than an amine technology. It's actually similar to the way in which hemoglobin binds oxygen from air. Once you start to capture CO2, it actually becomes more and more efficient to capture the next one. So you get the switch-like behavior for the capture process, where you actually either fully saturate or fully release the material of CO2 over a fairly narrow temperature range. We've been able to increase the capacity of the material that captures the CO2, that drives down the overall size of the plant needed, the amount of material needed. That CapEx consideration is one of the big drivers ultimately of capture costs, but it also reduces the OpEx, which is how much steam is it taking from the power plant, how much heat is overall required for the carbon capture process. We can operate in a much more efficient adsorption-desorption cycle range. We can close that temperature gap to about 60 degrees Celsius, and it really make the plant more efficient from the electricity generating side. Try to take advantage of waste heat has been a really successful approach that people have looked at for driving down the cost of carbon capture. You really need to tackle both the CapEx and the OpEx to get carbon capture technologies where they need to be. DOE's sweet spot is around $40 a ton for CO2. Over the next decade, as some of these technologies get to scale, we'll get pretty close to those numbers.
Yeah, this $40 a ton was one metric. I think I looked it up one time at some of the larger commercial carbon capture that's out there. The numbers I was coming up with for the CapEx was about $1.5 million per installed megawatt. Now, I may have been missing some things, but if you do a couple hundred megawatts, that turns into hundreds of millions of dollars.
Yeah, I think it's one of the reasons, going back to the importance of those ExxonMobil Energy Factor commercials, it's really important to increase the overall level of literacy that electricity and power in general is a very important and capital-intensive industry, and that's true for both current power plants that are creating electricity, but also the solutions that can hopefully address some of the carbon capture. I think it's a big challenge, the upfront CapEx of these, which is why we need to drive down the cost, and I believe it's one of the reasons why many of the emerging approaches like direct air capture will begin to have an increased level of prominence in the discussion. With some of those approaches, you don't have to build a full-size power plant at once to get a commercial iteration done. It allows you to have faster learning cycles, and through that faster learning cycle, ultimately, hopefully, drive down costs more efficiently than building a single large 550 megawatt power plant and seeing the final cost number get.
Right. That's an excellent point, because what you're describing here is a modular approach to this. You don't have to build something to prove concept. You don't have to capture 100% of the flue gas coming out. You can scale it up to prove concept. I think that's one of the things that really freaks out a lot of utilities, is this idea of, I don't want to be the first, and heaven forbid it doesn't work, right? It feels to me like you can dip your toes in to try this out. You don't have to build the whole thing at once.
Absolutely. And new technologies, I think, will play a really critical role in reducing that CapEx. It's one of the things about the transition, especially in the United States, from coal to natural gas, where there's just such a much greater variability in coal that ultimately it's hard to build a modular carbon capture type system. A lot of the natural gas combined cycle plants that are out there, because the natural gas is coming from the grid, there's a lot greater consistency to those types of plants, where I think moving towards a modular carbon capture approach, both on the point source side, becomes much more doable. I do believe that natural gas will increasingly have an important role in the overall dialogue about how do we effectively deploy carbon capture technologies. A lot of the economists and the policy folks that I follow and look at really believe that assets like carbon capture can help really accelerate the time frame of getting to net zero, which is really, I think, everyone's goal here, and also reduce the total cost of getting to a low carbon economy.
Yeah, one of the things that I talk about a lot on this show, I had a guest, Net Power. They have a pre-combustion carbon capture solution. But I think that one of the things that's important there is, even if we killed all the coal plants, a lot of this is going to get offset with natural gas. And I think that there really needs to be a stronger conversation about carbon capture for natural gas.
Yeah, I completely agree. And I think what's really exciting about technologies like Net Power, which is also a carbon capture approach, when you project out what is the most efficient way of building these power plants in the future, a lot of those more innovative processes should play an increased level of importance in dialogue as well. Adsorbents can play a really important role in reducing the cost of doing separations, whether it's pre-combustion, oxy-fuel, post-combustion. But a lot of the power plants, both the coal plants that have been built around the world in recent decades, and a lot of the natural gas plants that we're building in the U.S. and overseas, utilities' intention is to run those for many decades. Unless we efficiently come up with effective solutions for those assets, it's going to be a really tough road to get to net zero as quickly as we want to get there.
We're talking a lot about power plants right now. I do want to ask you about, you say on your website that not only are you working on an absorption solution for power plants, flue gas, for instance, you also are working on a metal organic framework, MOF, for natural gas that can separate the components of natural gas. It's not all one element. Explain why that is important. Natural gas is traditionally cracked, right? That's a pretty energy intensive process.
This would probably be a little bit different than the cracking side of natural gas. In that case, when natural gas comes out of the ground, or when we look at things like renewable natural gas, which comes from things like anaerobic digestion, so biogas, that natural gas has a fairly significant CO2 impurity in it. To ultimately get to the quality that's required to put into a pipeline, it needs to be removed of a lot of components: nitrogen, oxygen, hydrogen sulfide, but definitely CO2. It's actually probably the largest CO2 separation application. We believe that an important stepping stone to get to a full-scale carbon capture facility can also help us make that natural gas sweetening process much more energy efficient.
Sure, and it goes without saying that this sounds like it'd be very effective for LNG, which when I did my episode on that, I couldn't believe how much was involved in removing all the impurities so that you could liquefy it. Blew my mind.
Things like LNG production, the CO2 level has to be even much lower than going into a pipeline.
Yeah.
So these technologies become really important and will continue to be, especially as the United States moves towards being a natural gas exporter.
Thomas, getting to the commercial that brought this to my attention, how did ExxonMobil get involved?
A lot of the major oil and gas companies have been looking at carbon capture technologies for a long time now. My original interactions with ExxonMobil date back to grad school. We started an early collaboration as a grad student on these types of materials for post-combustion carbon capture. Ultimately, as a grad student and then at Mosaic, as we continued to improve the technologies, we maintained active discussions with a number of oil and gas companies, including ExxonMobil, and we found a really nice potential project for evaluating the use of our materials in a carbon capture type process that ExxonMobil has been looking at and trying to develop. It's been a really fun experience so far to go through and talk about how we can carry these technology forward. Ultimately, I believe that new technologies can be a really unifying force for ultimately getting the capital and technology that's required to bring a new materials technology to scale. People have been following our technology ever since we came up with it 6-7 years ago. And so it was nice for that to finally come to the point where we were able to finish an agreement, then publicly announce it earlier this year.
Your company was spun out of a university. That's interesting that Exxon was involved when you were back in school and Mosaic hadn't been founded yet. But what difference does the support of a super major like an ExxonMobil make when growing the company? And I think that it would also help with potential clients. There's a little weight behind the ball. You're taking a little bit more seriously, right? And they'll want to take risks on a technology that they've never tried before.
Yeah, I think that's absolutely true, because I do believe having the ability of companies to go and publicly say that they're interested in evaluating your technology is a really great way of showing the value of new technologies for solving really challenging problems. These are not easy problems to solve, carbon capture especially. Allowing people to express their interest in the promise of a new technology is a really great way of bringing attention and resources to companies like Mosaic, where it's important that we continue to advance the technology with a range of partners, especially ones who have the ability to offer fresh insight and engineering experience and scale-up experience to the types of problems that we're trying to solve.
What do you think Exxon is really after here? I think we think of them a lot as a conventional oil and gas company. We don't think too much about the power side with them.
I do believe that ExxonMobil is interested in advancing the technology readiness of a range of carbon capture solutions. And I think we see that from their public announcements of things like, I think, great collaboration with Fuel Cell Energy, Global Thermostat, and also Mosaic Materials. Deploying carbon capture technologies will absolutely, I think, be an essential role, basically helping the world meet the sustainability needs while recognizing that fossil fuels aren't going away anytime soon.
For Mosaic and this technology, the MOFs, what do you think is the low-hanging fruit? I would think post-combustion on existing plants. And of course, there's greenfield plants. I'm sure we're going to be building more of them, maybe not necessarily more coal plants right at this moment. But when you're looking at who the clients are going to be, where you're going to be selling this to, who are they?
That's definitely a tough one. I'm not sure I would call any of these low-hanging fruit. Our technology has a real advantage for post-combustion, getting technology to work effectively for post-combustion. New plants, especially if they're being built for a low-carbon economy, might ultimately go more towards pre-combustion or octa-fuel type technologies. But getting to the level required for post-combustion is definitely many years away. A number of markets we plan on trying to get there. Biogas, natural gas sweetening, a really exciting opportunity for Mosaic is the direct air capture space. In many ways, I think new plants are an easier problem to solve than existing plants because you can design for the carbon capture point already. Going through the challenge of reconfiguring a steam cycle and doing a rebuild is definitely not easy.
You mentioned some engineering challenges. I think many people who are listening to this go, this sounds great, sign me up. What challenges are you facing right now before we can see you guys going in and bolting on to an existing coal plant?
Mosaic's a company currently focusing on scaling up the technology to the level in which we can do some larger field pilots and working towards demonstration. We're a materials first company, making the best materials possible. Getting them out of the laboratory and towards multi-ton scale production is really one of the main efforts of the company over the next year. But ultimately, in continuing to integrate our materials into some novel processes that are coming out for how you would use a solid adsorbent in carbon capture. Dealing with things like heat transfer, I think, how do you effectively heat and cool a bed is a really important question. We have a number of collaborations in that area, of which ExxonMobil is one of them. We believe that our technology can make a lot of processes better, and so we're excited to have conversations with any number of people who would be willing to look at developing an innovative process that takes advantage of the unique materials properties we can offer.
Well, I'm sure a lot of people listening, this has stoked a lot of people's attention, so I sure hope you get some responses there. I'm curious, and I ask some people this every now and then whenever I do my coal stories. You went to UC Berkeley, you live in the Bay Area, you undoubtedly probably have dinners with people, and you explain the work you're doing. And what are some of the conversations that you have, especially with folks who are dialed into this idea that the only solution moving forward is renewable energy? You, like me, I lived in Austin, Texas, when I worked for the Clean Coal Group. I undoubtedly found myself in these kind of conversations. Tell me how those have gone and what your response has typically been.
Most people, I think, have come to recognize the serious threat that global warming, and I believe also ocean acidification. One of the things that I always like to offer back is that I'm a huge advocate for wind and solar increasing as fast as possible. But even as we've had an incredible build out in wind and solar, it's really only gone towards a lot of the increased use of energy. It's made only a very small dent in the amount of fossil fuels that we've been using, at least until recently. Without things like nuclear energy, hydroelectric, carbon capture, storage, combined with some fossil fuel plants, I think it will be really difficult to build out solar and wind and storage at the scale and in the timeline that we need to make sure that we don't go above our carbon budget. And if we do, to not go too far over, such that negative emissions technologies can play a role.
One of the things you mentioned at the very beginning, you chose this line of work, you went to grad school, you wanted to do something about CO2. Look, the podcast we do here is called Energy Cast. I like to focus on energy. But do you feel like we only focus on CO2 as it pertains to industry? What about removing the CO2 that's there? Experts say there's already too much. And when I hear a lot of people talk about climate change and CO2 emissions, it feels like they are preoccupied with doing something to hamper industry when we really need to be focusing, I think, a lot more on this idea of we probably need to take out what's already there in the atmosphere. Right? And I feel like this solution addresses that. You could probably do direct air capture, as you've talked about, right?
Absolutely. Yeah. One of the greatest potentials for our technology is to really dramatically reduce the cost of things like direct air capture, because it's an area where new adsorbents can have an outsized impact on the final economic numbers that you get for that. A ton of CO2 that's not in the atmosphere is a good thing. Whether that was a ton that was previously there and has been taken out and put underground, or it's a ton of CO2 that was prevented from going into the atmosphere in the first place by attaching point source carbon capture. Ultimately, I think the traditional belief has been the cost of keeping a ton of CO2 out of the atmosphere by doing carbon capture at a point source is cheaper than pulling that ton of CO2 out of the air. To scale out things like direct air capture and other negative emission technologies, the life cycle analysis becomes really important, because the last thing we want to do is for that to not have a negative impact at all. What is the energy mix that's feeding into it? Many of these technologies can be deployed on industrial sites. It's stationary, it's a really large concentrated source, and therefore the dollars per ton of getting it is much less than getting it from things like a car or an airplane. Getting that next ton becomes increasingly more expensive, and that's when we rely upon new technologies to bring down that cost as much as possible.
Thomas, that's great. I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Increasingly common.
Crude oil.
Near its peak.
Nuclear.
Too CapEx intensive.
Coal.
Not going away in India and China anytime soon, unfortunately.
I'm also add coal with carbon capture. You guys.
Really important, because it's not going away anytime soon in India and China.
Wind.
Offshore will be a big breakthrough. Yeah.
Solar.
Really powerful, especially with long duration storage.
Biofuels.
Huge potential and is really oftentimes overlooked.
Hydroelectric.
Also really overlooked in terms of creating clean power, but huge land issues.
Geothermal.
I think with energy breakthroughs could really be significant in terms of clean energy.
Yeah. Energy storage.
Long duration storage is so important and needs a lot of work on.
Electric vehicles.
Really important for not just reducing CO2 emissions, but also clean air.
Energy efficiency.
Need some policies that allow people to save money in the long run by doing things up front now.
And then finally, fusion power.
Would absolutely be amazing, but I don't think we shouldn't bet the world on hoping we figure it out, but I absolutely hope we do.
All right, Thomas McDonald, Mosaic Materials, thank you so much for your time.
Well, thank you, Joe. Had a good time.
That was Dr. Thomas McDonald, co-founder and CEO of Mosaic Materials, a Bay Area company developing metal organic framework technology for carbon capture. Thomas says their natural gas technology could make sweetening preferable to flaring natural gas, like we discussed in episode 64. He also says another business opportunity is life support applications, scrubbing CO2 out of the air for the Navy and NASA. I want to thank Thomas for his time and for setting this up. You can find plenty of pictures on energy-cast.com, as well as on Instagram at Host Energy. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 74. Be sure to join us next week when I catch up with a guest at New Orleans' PowerGen show who is developing a renewable hybrid energy system based on their long-running diesel generator technology. Until then, I'm Jay Downhauer. We'll see you next time.